Calculate the pure component boiling points, there they are. And then we can calculate, as you have in your notes, written out, x1 is equal to this quantity, evaluated, it can be evaluated for each temperature. And if I plug in the P that was given as 1 bar, then this is what it is. So here we just need to calculate the vapor pressures for each temperature. Once we've got that, I can calculate Y1 and hence get X1 as well. And here's the spreadsheet that I have for that, and here are the resulting curves. Any question about that one? Problem 2, you're assuming the VLE system of benzene, toluene, and styrene obeys Raoult's law. Evaluate the pressure, that would be a bubble point pressure. Sorry, and the dew point pressure and the liquid phase composition at a temperature of 373.2 K and Y1 equals 0.2 and Y2 is 0.5. So there's a ternary system, so that's one little wrinkle that's different from what I had done in class, but I had the layout for this situation plotted out for you in the handout. So our dew point pressure is expressed this way when we sum the mole fractions in the case of unknown composition equal to 1. The 3 component vapor pressures are all calculated out of the Antoine constants that are supplied in the Koretsky appendix. And here they are, the numbers, from which I can just plug in and solve for the final pressure, 0.514 bar. And then I can use Raoult's law to calculate the resulting x's, and there they are. And once we've calculated them, it's a good idea to check to see if they in fact sum to unity, which they do to an acceptable extent here. Any question about this? In part 2, you're given T and the vapor phase composition at a pressure of 1 atmosphere. And you want to calculate, T and the vapor phase composition, given that the pressure is 1 atmosphere and the liquid phase composition is given here. So what we want is the bubble point temperature. Now this is a situation where it's convenient to iterate, particularly here since we have a ternary system. And I chose to iterate, as I indicated in the lecture notes, to iterate on the first vapor pressure, but you could have chosen either of the other two. But if I iterate on the first vapor pressure, I will isolate that and express it in terms of these relative volatilities. And the relative volatilities are from their definitions given here in terms of the logarithms. This is a case of Raoult's law, so we don't need to bother with activity coefficients, and the expressions reduce as I've shown here. So we start the iteration. It's not very sensitive since it converges very rapidly, but I started the iteration at 380. And then you calculate, first of all, the alphas, then you calculate the vapor pressure that you're going to iterate on. And once you've got that, you can invert it to get the next value of temperature to continue the iteration until it converges. So the new temperature is calculated here from inverting the component 1 Antoine equation. Here's what that looks like. And here's the resulting spreadsheet. And it converges from E to 394. Once we've got that, I can evaluate the vapor pressures. You could go back to the Antoine equations to evaluate them, but a simple way is just to take the values off the spreadsheet for the alphas and calculate them this way. But in any case, here they are. These are all in bar. That lets me calculate the y's from the Raoult's law for each of the components, and here they are. And once we've got them calculated, we can see, again, if they sum to unity. And looks like we're okay. Okay, so third problem, we've got flash point of a liquid fuel is the liquid temperature at which the concentration of the fuel vapor in air is large enough for a flame to flash across the surface of the fuel if an ignition source is present. And the values that we get for this are obtained by experiments, lab experiments that will give us what that is. And for methanol, this concentration corresponds to 6.7 mole percent. And that would be the mole percentage concentration in the vapor mixture, which is going to be a mixture of air, methanol, and perhaps water vapor. but this is the key point. You're asked to estimate the flash point of the methanol water solutions at 1 atmosphere total pressure and to prepare a plot of the flash point, that would be the temperature, versus the mole fraction of methanol. And you could guess that the higher the concentration of methanol would be, then the lower would be that flash point temperature. Going down finally, if I had pure methanol, then I would have a minimum value for that flash temperature. And if I go to 0 methanol, then of course that temperature would go to infinity. Now the activity coefficient for methanol in water, in the methanol water solution is given by this expression, log gamma 2 is equal to 0.788 x1 cubed. So a little bit different here we've got a different exponent here. So the piece of information that you have that you want to work from to get this flash point temperature as a function of composition is the stated fact that Y2 is 0.067. And if I've got atmospheric pressure here, I'll multiply that by 1 atmosphere, which is 1.0133 bar. So that's 0.06776 bar. Now I can write the vapor-liquid equilibrium equation for the methanol, because I know I now know this value, and so I'll equate it to the fugacity in the liquid phase, which is the activity coefficient here times x2 times the vapor pressure, which is a function of temperature. So when I plug in the value for gamma 2 is exponential here, 0.788 x1 cubed, then I've got x2 times p2s just from this equation. So we're making an assumption here that the activity coefficient is going to be effectively independent of temperature over the range, which is an approximation, but the only thing we can do here because we don't have any more information. The vapor pressure here given from the Antoine equation out of the appendix. So now I just plug back up into this equation, and I've taken the log of both sides to do that. So log 0.06776 goes to, now you look up here, okay, 0.788 x1 cubed plus log of x2 plus log of p2s. Or I can rearrange that as follows and then plug in for log p2s from the Antoine equation. So what I recognize here is that what I've ended up with is an equation that relates T to x2, and that's exactly what I want. That's the flash point temperature as a function of x2. It turns out in this case I can rearrange it to have an explicit expression for the temperature, there it is, and then plot that. Any question about this? And of course it's a reminder that when you're working with flammable solvents, you've got to be careful about what this is. So it's another PSA type problem.
What was the flash point temp for the first? I missed it. What was the?
Excuse me?
What was the flash point temp for the very first? The first part of the problem.
Well, you can. They're all given in that plot. I'm looking for what you're asking.
It says, fourth line down, estimate the flash point of methanol water solutions at 1 atmosphere. Oh, I thought you wanted us to get a specific flash point and then plot.
I didn't do that. I just said to plot it.
Okay.
So any specific value you want, you can pull off this plot. Anything else? Okay, let's look at the next one. You're asked to evaluate the bubble point pressure of an equimole of water methanol solution of 25C. Make use of the activity coefficient information from the previous problem. So once again, here we've got this expression for the total pressure, which is using the modified Raoult's law as the sum of the two contributions to the partial pressure from the two components. But now what we have is this, and what we need is gamma 1 in order to complete this evaluation. So we know from the Gibbs-Duhem equation, if I have complete knowledge of one of the activity coefficients, I can derive the other. And that's what you need to do here. And now what we know is gamma 2 is a function here of composition, so we need to derive it for gamma 1. So you just flip the subscripts from what you have in the notes. And the equation we have from the CHEME equation is this. So I need to evaluate d log gamma 2 dx2, so I look up here and do that.
Doctor,
And that turns out to be minus 2.364 times x1 squared, yeah.
the equation that you have for gamma 2 is just 0.788 x1.
Did I make a mistake somewhere?
You have log of gamma 2 is equal to 0.788 x1 cubed.
No, I think this is
Okay.
what I've got. You want me to go back and look?
Yeah. You just check it out. I sure did.
There it is. Management here. So now I can derive d log gamma 2 dx2. There that is, that goes in up here, giving me this integral, which I now can evaluate. It's just pretty straightforward. I will be able to cancel out one of the x1s, and I end up with the integral here of x1, x2, dx2, from 0 up to some indefinite x2. I can write this in terms of x2 alone, then integrate it, getting this, ending up finally with an expression for log gamma 1 that looks like this. So now at x2 point is equal to 0.5, I can evaluate both gamma 1 and gamma 2. That. Plug them back into the equation and use the vapor pressures that I can get from the Antoine expressions. I had one of them already from the last problem. Now I can get the second one. And then finally I have everything I need to know to plug in to get the pressure here, 0.11 to a bar. Any questions about this? In the last problem, we have the following daily data for the carbon disulfide chloroform system at 25C. So there it is, and what you're asked to do is to find the best fitting Margulis parameters for this data set and to use them to prepare a PXY diagram and compare that with the experimental points to see how well we did with that correlation. Okay, from these data we can prepare a spreadsheet, and then using the modified Rolle's law point by point we can evaluate the respective activity coefficients and then compute for each the excess gives energy over RT. Then we finally compute this function, and we can see how well we can fit that to a straight line using linear regression. That all works out to look like this when I do it for all of the numbers in the spreadsheet. And so this is what I'm ultimately going to look at and find out how good a straight line I'm going to be able to get for that. And it turns out to be excellent. I've got one little aberrant point there, but the rest of them really fit very, very well to a straight line. And out of that straight line, I can extract the Margulis parameters A12 and A21 according to the formula that I gave you in class. And there they are. So now we have everything we need to know to actually derive the expressions for log gamma 1 and log gamma 2. And here they are plotted up. And the values for log gamma 1 and log gamma 2 that I calculated out of the modified Raoult's law, point by point, are shown here plotted. So you can guess that the ultimate plot here is going to show very good agreement with the data. So we use the Margulis equations with these constants to predict the gamma, calculated values of gamma, and that's actually what I use to make these curves. There are the algebraic functions for it, and then I can calculate y. So I made additional columns here in the spreadsheet for the calculated values that can ultimately be compared back. This pressure, for example, can be compared here, and y calculate can be compared with the y that we have in the data set. And when I prepare the plot of that, it looks really good. The predicted curves appear to go right through the data points. This is the last problem, so any question about anything in the problem set here? Okay, I think we're done for today. Do I have everybody's problem set turned in?